Hello everyone. Today we'll study areas and arc lengths in polar coordinates. First of all, before we talk anything in polar coordinates, let me review two things for you. How do we find area of a circular sector? How do we find area of a circular sector? Suppose that's a circle. That's a circular sector of a circle. That's a circular sector of a circle. Assume the angle here is theta. And the radius of the circle is r. How do we find the area of the circular sector? We know that the area from the entire circle is pi r squared. If we observe the picture, we can see that the ratio of the area between the circular sector and the entire circle is the same as the ratio of their central angles. So the ratio of their area is the same as the ratio of their central angle. That means if we try to find the area of the circular sector, we take the area of the entire circle multiplied by the ratio of their central angles. I'll get the area of this circular sector. So I take the area of the entire circle multiplied by the ratio of their central angles. The central angle for this circular sector is theta. And the central angle for the entire circle is 360 degrees. The central angle for the entire circle is 360 degrees. So that's the ratio of their central angles. If I take the area of the entire circle times the ratio of their central angle, I get the area of the circular sector. Now, 360 degrees in radial measure is 2 pi. If we write 360 degrees in radial measure, that's 2 pi. If we write 360 degrees in radial measure, that's 2 pi. So the area of the circular sector is, if I cancel pi here, I get half of r squared theta. If I cancel pi here, I get half of r squared theta. That's the area of the circular sector. Next, let me review how to find the area under a curve. Let f of x be a continuous function. On the interval from a to b. Find the area under the curve. From x equal to a to s equal to b. Let f of x be a continuous function on the closed interval ab. Find the area under the curve y equal to x from s equal to a to s equal to b. Let me show you the picture first. Suppose that's the function y equal to f of x. We're looking for the area under the curve from a to b. Assume that's a, that's b. How do we find area under the curve? We first of all divide interval ab into n subintervals. We first of all divide interval ab into n subintervals. Then a will be x0, b will be xn. The partition here is s1, s2, x3, x sub I minus 1, x sub I. The second last one is x sub m minus 1. Here we divide interval ab into n subintervals. Assume the width of each subinterval is the same. Assume the width of each subinterval is the same. Then the width of each subinterval delta x can be written as b minus a over n. B minus a is the length of the entire interval. The total length divided by the number of subinterval is the length of each subinterval. Assume the length of each subinterval is delta x. That's how we find delta x. Next, on each subinterval, we pick sample point. On each subinterval here, we pick sample point. Suppose in the first subinterval, I pick x1 star. In the second interval, I pick x2 star. Next one, I pick x3 star. Sample point could be any point on the interval. Sample point could be any point on the interval. Then in the ith interval, I pick xi star. On the last subinterval, I pick xn star. Next, we use the sample point to approximate the height. We use sample point to approximate the height. Next, f of x1 star. We use a sample point to approximate the height of a rectangle. That's f of x2 star. We use sample point to approximate the height of each rectangle. That's f of x3 star. That's f of xi star. The last one, that's f of xn star. Here we can see that the area of each rectangle is very close to the area under the curve in this subinterval. The area for each rectangle is very close to the area under the curve on each subinterval. Next, we can try to find area for each rectangles. Area of each rectangle is length times width, or width times the height. Area for each rectangle is width times the height. So area for each rectangle is width times the height, or height times width. F of Si star is the height. The width is delta x. That's an area of each rectangle. The width times the height. Width times height. Height times width. That's the area of each rectangle. If we add them up, taking the sum for I from 1 to n, we can approximate the area under the curve. If we add them up, we can approximate the area under the curve. Then, in order to get the actual area, we must take a limit as n goes to infinity. As n goes to infinity, we find the actual area under the curve because the width of each rectangle will be very, very small, and the area of each rectangle will be very, very close to the actual area under the curve. So once we take a limit as n goes to infinity, we get an actual area under the curve. This formula is called Riemann sum. This is called a Riemann sum. And by the definition of definite integral, this limit with Riemann sum can be written as integral from a to b, f of x dx, integral from a to b. When we apply definition of definite integral, f of si star become f of x, delta x become dx. That's the actual area under the curve. Next, let's talk about area in polar coordinates. Let r equal to f of theta be a continuous polar curve. Find the area from the polar curve. Find the area from the curve r equal to f of theta to the origin. For theta is between alpha and beta. Find the area from the curve r equal to f of theta to the origin. For theta is between alpha and beta. Let me show you the picture first, how it looks like. Let me show you the picture first. Assume that's a polar curve, r equal to f of theta. Assume that's a polar curve, r equal to f of theta. Assume the origin is here. We're looking for area from the curve to the origin. Assume that's alpha. Angle alpha is here. Assume that's angle beta. We are looking for area from the curve to the origin. For theta is between alpha and beta. That's what we are looking for. We are looking for this area here. Now, how do we find area here? We first of all divide this angle. I first of all divide this angle into n sub-angles. I first of all divide this angle into n sub-angles. Assume that's theta 1. Of course, alpha is theta 0. Assume that's theta 1. Assume that's theta 2. Then assume some angle in the middle. Assume some angle in the middle is theta sub I minus 1. That's theta sub I. And the last one is beta is theta n. The second last one is theta sub n minus 1. So here I divide this angle into n sub-angles. I divide this angle into n sub-angles. Assume the measure of every sub-angle is the same, called delta theta. Assume the measure of every sub-angle is the same, called delta theta. Then delta theta equal to the total measure, beta minus alpha, divided by the number of sub-angles. That's the total angle measure, beta minus alpha. That's the total angle measure, divided by n sub-intervals. That's delta theta. Next, for each region here, we try to use a circular region. We try to use a circular sector to approximate the area. For each region here, we try to use a circular sector to approximate the area. For example, in the first region here, I pick sample point called theta 1 star. In the first region here, pick sample point called theta 1 star. Theta 1 star on the curve is f of theta 1 star. Theta 1 star is between theta 0 and theta 1, and the point on the curve is f of theta 1 star. Then we use theta 1 star to draw a circular sector. We use theta 1 star to draw a circular sector, and use circular sector to approximate the area here. In the second interval, I pick sample point called theta 2 star. Theta 2 star on the curve is f of theta 2 star. Then use this point to draw a circular sector. Then use this circular sector to approximate the area. Then we use this circular sector to approximate the area. And here, between theta I minus 1 and theta I pick sample point called theta I star. Theta I star on the curve is f of theta I star. Theta I star on the curve is called f of theta I star. Now I use this point to approximate the area of this circular sector, of this region. And we use a circular sector to approximate the area of this region. So for every region, we pick sample point. The last one is f theta n star. Last one is f theta sub n star. Then we use this point to draw a circular sector and use the area of the circular sector to approximate the area of each region. Now we can see that the area of each circular sector is very clear, it's very close to the area of each region. It's very close to the area of each region for the area between the curve, area from the curve to the origin. Next, we want to find the area for each subregion. Look at a typical one, look at this one. For this one here, this is a circular sector. Area for circular sector is half of the radius squared times the central angle theta. Here we know that the central angle of this circular sector is delta theta. That's the central angle of this circular sector. How about radius? Radius is f of theta I star. Since we use f of theta I star as a radius to draw the circular sector, radius of this circular sector is f of theta I star. F of theta I star, that's the radius of this circular sector. Then we square the radius, and then times half. That's the area of this circular sector. That's the area of this circular sector, which is very close to this region here. Which is very close to the area of this region here. Then for a total area, I take the sum as I from 1 to n. For a total area, I take the sum as I from 1 to n. This is the approximate area for an area from the curve, from the polar curve to the origin. For theta is between alpha and beta. That's an approximate area. It's not the actual area, but that's an approximate area. This is the Riemann sum. This is the Riemann sum. If I take limit for the Riemann sum, I get an actual area. If I take limit, that means I make each subangle to be very, very small. I get an actual area from the curve to the center, to the origin. For theta is between alpha and beta. If I take limit, I find the actual area from the curve to the origin. Then, by definition of definite integral, if I take limit for Riemann sum, I got an integral for theta from alpha to beta. Half of f of theta I star become f of theta. F of theta I star become f of theta. Square stays the same. Delta theta become d theta. That's an area from a polar curve to an origin. For theta is between alpha and beta. Keep this formula in mind. This formula sometimes can be written as area equal to theta from alpha to beta half of r squared d theta. Sometimes f of theta is the same as r. Right, r is a little simpler, so it can also be written as area is integral from alpha to beta half of r squared d theta. That's an area from a polar curve to an origin for theta between alpha and beta. Sorry, here theta should be from alpha to beta. Theta should be from alpha to beta. Next, let's do some examples. First example, let r equal to 2 cosine theta be a polar curve. Find the area from the curve to the origin for theta is between 0 and pi over 2. So use the area formula. Area is integral from alpha to beta half of r squared d theta. Alpha and beta here is 0 and pi over 2. R is 2 cosine theta times d theta. Then solve this integral. If I distribute square, 2 squared is 4. 4 times half is 2. And distribute square to cosine, I get cosine square of theta, d theta. For cosine square of theta, I can use half angle identity. For cosine square of theta, I can use half angle identity, which is half of 1 plus cosine 2 theta d theta. Use half angle identity for cosine square theta. I get half of 1 plus cosine 2 theta. 2 times half is 1. They get cancelled. So I get 1 plus cosine 2 theta d theta. Next, take antiderivative. Antiderivative of 1 is theta. Antiderivative of cosine 2 theta is half of sine 2 theta. Then evaluate when theta is from 0 to pi over 2. If I plug in pi over 2, I get pi over 2 here for theta. If I plug in pi over 2 for theta here, 2 times pi over 2 is pi. Sine pi is 0. I get 0. If I plug in 0, I get 0. Then I get pi over 2 plus 0 minus 0, which is pi over 2. Next, let r equal to tangent theta be a polar curve. Find the area from the curve to the origin for theta is between pi over 6 and pi over 3. So we use the formula. Integral from alpha to beta half of r squared d theta. Alpha is pi over 6. Beta is pi over 3. R is tangent theta d theta. Take antiderivative. I can pull out half first. Tangent squared theta. How can we take antiderivative for tangent squared theta? Tangent squared theta can be rewritten as secant squared theta minus 1 d theta. Because there's strict identity says tangent squared theta plus 1 is secant squared theta. If we solve this equation for tangent squared theta, we get secant squared theta minus 1. Then take antiderivative. Antiderivative of secant squared theta is tangent theta. Antiderivative of 1 is theta. Evaluate from pi over 6 to pi over 3. Then plug in pi over 3 and pi over 6, take difference. If I plug in pi over 3, tangent pi over 3 is radical 3. Theta by itself is pi over 3. If I plug in pi over 6, tangent pi over 6 is radical 3 over 3 minus theta. Theta by itself is pi over 6. Then multiply out. Combine like term first. Radical 3 minus radical 3 over 3 is 2 radical 3 over 3. Pi over 3 minus pi over 6 is pi over 6. Then distribute half. We have radical 3 over 3 minus pi over 12. Next example, let r equal to 1 minus sine theta be a polar curve. Find the area enclosed by the polar curve. What does it mean, area enclosed by the polar curve? Let's draw the picture first. We'll see how it looks like. Let's draw the picture first. So let's make a table, draw the picture. Make table for r and for theta and r. Let's try some value for theta. Try 0, pi over 2, pi, 3 pi over 2, and 2 pi. Then find r. If I plug in 0, sine 0 is 0, I get 1. If I plug in pi over 2, sine pi over 2 is 1. 1 minus 1 is 0. If I plug in pi, sine pi is 0, I get 1. If I plug in 3 pi over 2, sine 3 pi over 2 is negative 1. 1 minus negative 1 is 2. If I plug in 2 pi, sine 2 pi is 0. 1 minus 0 is 1. Next, let's sketch a graph. When theta is 0, r is 1. When theta is 0, r is 1. When theta is pi over 2, r is 0. Theta from 0 to pi over 2. Then when theta is pi, we are here. When theta is pi, r is 1. When theta is 3 pi over 2, r is 2. When theta is 2 pi, r is 1. 2 pi go back to 0. R is 1. We are here. That's a heart shape. That's a heart shape. So when theta from 0 to 2 pi, this curve complete one cycle. For theta from 0 to 2 pi, this curve complete one cycle. So for the enclosed area, we take integral. For theta from 0 to 2 pi. For theta from 0 to 2 pi, complete one cycle. Half of r squared, r is 1 minus sine theta squared d theta. Then take integral. Expand the perfect square first. We get 1 minus 2 sine theta plus sine square theta d theta. We can pull out half first. Then I get 1 minus 2 sine theta. For sine square theta here, we can use half angle identity. So we can use half angle identity for sine square theta. That can be written as half of 1 minus cosine 2 theta. Then distribute half. 1 minus 2 cosine theta. If I distribute half, I get half minus half cosine 2 theta d theta. If I combine like terms, 1 plus half is 3 half. Minus 2 cosine theta minus half of cosine 2 theta d theta. If I distribute half back, If I distribute this half back, integral is from 0 to 2 pi 3 over 4 minus cosine theta minus 1 over 4 cosine 2 theta d theta. Then I take antiderivative. I get 3 over 4 theta. Antiderivative of cosine theta is sine theta. Antiderivative of cosine 2 theta is half of sine 2 theta. Then evaluate for theta from 0 to 2 pi. If we plug in 2 pi, we get 3 over 4 times 2 pi. Sine 2 pi is 0. Sine 4 pi is also 0. If I plug in 0, I get 0. So the answer is 3 over 4 times 2 pi, which is 3 over 2 pi. That's an area enclosed by the polar curve. That's an area enclosed by this heart shape. Next example, let r equal to sine 3 theta be a polar curve for an area enclosed by one of the leaves. What does it mean, one of the leaves? Let's draw the picture first, then we'll see what does it mean. R equal to sine 3 theta. Let's make a table for theta and r. What should we choose value for theta? Here, let's try to make 3 theta equal to pi over 2. Then theta is pi over 6. Let's try to use pi over 6 as a step for theta. So 0, pi over 6, 2 pi over 6, which is pi over 3. 3 pi over 6 is pi over 2. 4 pi over 6 is 2 pi over 3. 5 pi over 6. 6 pi over 6 is pi. Let's try this point first. We may need more points. Let's try this point first. If we plug in 0, sine 0 is 0. If I plug in pi over 6 times 3 is pi over 2. Sine pi over 2 is 1. If I plug in pi over 3 times 3 is pi. Sine pi is 0. If we plug in pi over 2, 3 times pi over 2 is 3 pi over 2. Sine 3 pi over 2 is negative 1. If I plug in 2 pi over 3, 3 times 2 pi over 3 is 2 pi. Sine 2 pi is 0. If I plug in 5 pi over 6, 5 pi over 6 times 3 is 5 pi over 2. Sine 5 pi over 2 is 1. If I plug in pi, I get sine 3 pi. Sine 3 pi is 0. Let's try this point first. We may need more points, but let's try more point first. Let's try this point first. We may need more points. When theta is 0, r is 0. When theta is 0, that's in a positive direction, r is 0. We are in the origin. When theta is pi over 6, that's in a positive direction. When theta is pi over 6, r is 1. Assume that's 1. When theta is pi over 3, r is 0. Pi over 3 is here. R is 0, so go back to 0. Start from this point, go to this point, and go back to 0. It looks like this. And that's the direction as theta increases. Let's continue. When theta is pi over 2 is here, and that's in a positive direction. When theta is pi over 2 is here. That's in a positive direction. Here r is negative 1. R is negative 1, so this way is positive. The other way must be negative. So that's r equal to negative 1. Then when theta is 2 pi over 3, we are here. That's in the positive direction, 2 pi over 3. R is 0. We go back to origin. Let's continue the curve. From this, let's continue the curve From this point to this point, then go back to 0. Connect points using smooth curves. Then go back to 0. Connect points using smooth curves. Next, let's continue. When theta is 5 pi over 6, when theta is 5 pi over 6, r is 1. So somewhere here. When theta is pi, r is 0. We go back to origin. We go back to origin here. So from this point, go to this point, and go back to origin. Let's follow the path. Let's continue the curve, follow the path. If the curve continue, it goes this way. Connect 3 points using smooth curves. If the curve continue, it goes this way. Then it goes back to 0. Go back to origin. So that's the direction. Do we get everything here? Just to be safe, let's test one more point. If we repeat, then that's the entire graph. If it doesn't repeat, we need to plot more points. Let's test one more point. If I plot in 7 pi over 6, 7 pi over 6 times 3 is 7 pi over 2. Sine 7 pi over 2 is negative 1. 7 pi over 6 is somewhere here. That's the direction. Theta equal to 7 pi over 6. R is negative 1. This is positive direction. When theta is 7 pi over 6, this is positive direction. If R is negative 1, it should be here. So it repeats itself. The curve repeats itself. So start from 7 pi over 6, the curve repeats itself. So don't need this part. From 0 to pi, the curve complete one cycle. From 0 to pi, the curve complete one cycle. That's the path here. From 0 to pi, the curve complete one cycle. In this picture, you can see that there are 3 leaves. There are 3 leaves here. In the picture, you can see that there are 3 leaves here. The question is asked, find the area enclosed by one of the leaves. So let's find area enclosed by this leaf. That's the first one. That's the first one we drew. Let's find the area enclosed by this leaf. For this leaf, when theta is 0, we are here. Theta is pi over 6, we are here. When theta is pi over 3, we go back to origin. So for theta from 0 to pi over 3, we complete one leaf. For theta from 0 to pi over 3, we complete one leaf here. So take an integral. For theta from 0 to pi over 3, we complete one leaf. For theta from 0 to pi over 3, we complete one leaf. The formula is half of r squared. R is sine 3 theta. So we have half of sine 3 theta squared d theta. Let's solve the integral. For sine squared 3 theta, we can use half angle identity. It's half of 1 minus cosine 6 theta d theta. Here we use half angle identity because sine squared x is half of 1 minus cosine 2x. Here x is 3 theta. If I plug in 3 theta for x, 2 times 3 theta should be 6 theta here. So we use half angle identity for this part, for sine squared 3 theta. Then half times half is a quarter. Distribute a quarter. Distribute a quarter, we get a quarter minus a quarter times cosine 6 theta. d theta. Then take antiderivative. We get 1 over 4 theta minus 1 over 4 times 1 over 6 sine 6 theta. Take antiderivative. Evaluate for theta from 0 to pi over 3. If we plug in pi over 3, we get quarter times pi over 3. If I plug in pi over 3 here, 6 times pi over 3 is 2 pi, sine 2 pi is 0. Minus, if I plug in 0, everything is 0. So the answer is pi over 12. That's an area enclosed by one of the leaves. That's an area enclosed by one of the leaves. Next example, let r equal to 1 plus 2 cosine theta be a polar curve. Find the area of the inner loop. What does it mean, the inner loop? Let's sketch the graph. Let's sketch the graph first. We'll see what's the inner loop. Here the graph is r equal to 1 plus 2 cosine theta. Let's make a table for r and theta. Theta and r. Let's take theta to be 0, pi over 2, pi, 3 pi over 2, and 2 pi. Let's try this 5 point first. We may need more points. If we can sketch a smooth curve, we may need more points. Let's try this 5 point first. When theta is 0, cosine 0 is 1. 1 plus 2 times 1 is 3. When theta is pi over 2, cosine pi over 2 is 0. 1 plus 0 is 1. When theta is pi, cosine pi is negative 1. 2 times negative 1 is negative 2. 1 plus negative 2 is negative 1. When theta is 3 pi over 2, cosine 3 pi over 2 is 0. 1 plus 0 is 1. When cosine is 2 pi, when theta is 2 pi, cosine 2 pi is 1. 1 plus 2 times 1 is 3. Then let's plot points. When theta is 0, 0 is here. That's in the positive direction when theta is 0. R equal to 3. 1, 2, 3. The point is here. That's the point when theta is 3. When theta is pi over 2, that's pi over 2. R is 1. This is positive direction. 1 is here. The third point, when theta is pi, pi is here. That's in the positive direction of pi. R is negative 1. Positive 1 is here. So this point is negative 1. So when theta is pi, r is negative 1. Can we connect these 3 points using smooth curves? If we connect these 3 points using smooth curve, something looks like this. This point, this point, this point. If we connect using smooth curve, we get something looks like this. Now, does the curve go through an origin? Does the curve, if we connect a smooth curve like this, does the curve go through an origin? Does the curve go through an origin? Let's test it. If I set r equal to 0, and I find a solution for theta, that means the curve does go through an origin. But if there's no solution for theta, that means r can never be 0. If r can never be 0, means the curve never goes through an origin. So let's test it. Let's test if the curve will go through an origin. Set r equal to 0. When the radius is 0, the curve will go through an origin. Set r equal to 0, we have 1 plus 2 cosine theta equal to 0. If I can find a solution for theta, that means the curve will go through an origin. Otherwise, the curve doesn't go through an origin. Solve the equation for theta. Here we have cosine theta equal to negative half. Then solve for theta. Let's find the reference angle first. Reference angle is inverse cosine of half. reference angle theta is inverse cosine of half. Since reference angle is always positive, when we take a reference angle, we must drop negative sign. We know that cosine pi over 3 is half. So the reference angle is pi over 3. Now, cosine function here is negative. We know that cosine is negative in quadrant 2 and quadrant 3. So there are two cases. Theta could be either in quadrant 2 or quadrant 3. If theta is in quadrant 2, how do we find angle theta? If theta is in quadrant 2, how do we find angle theta? If theta is quadrant 2, angle theta is pi minus the reference angle. And the reference angle is pi over 3. Pi minus pi over 3 is 2 pi over 3. If angle theta lies in quadrant 3, how do we find theta in quadrant 3? In quadrant 3, angle theta is pi plus the reference angle. In quadrant 3, angle theta is pi plus the reference angle. So pi plus pi over 3 is 4 pi over 3. That means when theta is 2 pi over 3 and 4 pi over 3, r is 0. When theta is 2 pi over 3, 4 pi over 3, r is 0. So let's plot two more points. 2 pi over 3 and 4 pi over 3. Pi over 2, then 2 pi over 3, pi, 4 pi over 3, plot two more points. Then for the rest, keep the rest. 3 pi over 2 and 2 pi. When theta is pi over 2, cosine pi over 2 is 0, I get 1. When theta is 2 pi over 3, I get 0. When theta is pi, cosine pi is negative 1. 1 plus 2 times negative 1 is negative 1. When theta is 4 pi over 3, I get 0. When theta is 3 pi over 2, I get cosine 3 pi over 2 is 0. 1 plus 0 is 1. Then the last one, 2 pi. I don't have space here. When theta is 2 pi, I get 3. That's the last row. I don't have space. I put it here. That's the last row. Then let's plot points. Let's start over. First point, when theta is 0, r is 3. We are here. Second point, when theta is pi over 2, r is 1. We are here. Third point, when theta is 2 pi over 3, it's 2 pi over 3. When theta is 2 pi over 3, r is 0. Now connect these 3 points using smooth curve. That's easier. Connect these 3 points using smooth curves. Connect 3 points using smooth curves. Then when theta is pi, r is negative 1. We are here. Connect 3 points using smooth curves. Connect 3 points using smooth curves. When theta is 4 pi over 3, r is 0. It goes back to 0. Continue the curve. In this direction, continue the curve. when theta is 3 pi over 2, that's 3 pi over 2. This is 4 pi over 3. 3 pi over 2 is here. When theta is 3 pi over 4, it's 4 pi over 3, it's 3 pi over 2. When theta is 3 pi over 2, r is 1. So connect 3 points using smooth curves. Then last one, when theta is 2 pi. When theta is 2 pi, r is 3. 2 pi go back to 0. R is 3, the point is here. So it completes one cycle. When theta from 0 to 2 pi complete one cycle. That's the path of the curve. Now, try to find the area of the inner loop. That's the inner loop. For the inner loop, it starts from origin and ends at origin. Start from origin, end at origin. So when we start the inner loop, theta is 2 pi over 3. When we start the inner loop, theta is 2 pi over 3. When we complete the inner loop, we go back to the origin, and theta here is 4 pi over 3. So when theta is 2 pi over 3, we start the inner loop. Then continue. When theta is 4 pi over 3, we complete the inner loop. So for area enclosed by the inner loop, we take theta from 2 pi over 3 to 4 pi over 3. That's where we start the inner loop, and that's where we complete the inner loop. So for area enclosed by the inner loop, take integral for theta from 2 pi over 3 to 4 pi over 3. Area formula is half of r squared. R is 1 plus 2 cosine theta squared d theta. Then take an integral. One plus 4 cosine theta plus 4 cosine square theta d theta. If I distribute half, I get half plus 2 cosine theta plus 2 times cosine square theta d theta. Then if I apply half angle identity, I have half plus 2 cosine theta plus 2 times half of 1 plus cosine 2 theta d theta. That's half plus 2 cosine theta. 2 times half is 1. So I have 1 plus cosine 2 theta here, d theta. Half plus 1, if I combine like terms, half plus 1 is 3 half. Plus 2 cosine theta plus cosine 2 theta d theta. Next, take antiderivative with respect to theta. I get 3 over 2 theta plus 2 sine theta plus half of sine 2 theta. Evaluate from 2 pi over 3 to 4 pi over 3. If I plug in 4 pi over 3, I get 3 over 2 times 4 pi over 3. If I plug in 4 pi over 3 here, what do we get? I get sine 4 pi over 3. What's sine 4 pi over 3? 4 pi over 3 terminates in quadrant 3. Sine function in quadrant 3 is negative. Reference angle for 4 pi over 3 is pi over 3. Sine pi over 3 is radical 3 over 2. So Sine 4 pi over 3 is negative radical 3 over 2. If I plug in 4 pi over 3 here, I get sine a pi over 3. 2 times 4 pi over 3 is a pi over 3. A pi over 3 is more than one cycle. A pi over 3 is more than one cycle. So I find a coterminal angle. Take a pi over 3 minus 2 pi, which is 2 pi over 3. That means sine a pi over 3 is the same as sine 2 pi over 3. For sine 2 pi over 3, 2 pi over 3 terminates in quadrant 2. Sine function in quadrant 2 is positive. Sine function in quadrant 2 is positive. And for 2 pi over 3, reference angle is pi over 3. Sine pi over 3 is radical 3 over 2. That's what we get when I plug in 4 pi over 3. Now when I plug in 2 pi over 3, I have 3 over 2 times 2 pi over 3. 2 times sine 2 pi over 3. 2 pi over 3 terminates in quadrant 2. Sine function in quadrant 2 is positive. And for 2 pi over 3, reference angle is pi over 3. Sine pi over 3 is radical 3 over 2. Then here, if I plug in 2 pi over 3, 2 times 2 pi over 3, 4 pi is 4 pi over 3. 2 times 2 pi over 3 is 4 pi over 3. 4 pi over 3 terminates in quadrant 3. Sine function in quadrant 3 is negative. Then for 4 pi over 3, the reference angle is pi over 3. Sine pi over 3 is radical 3 over 2. Then adding up. Here I cancel 3. 4 divided by 2 is 2. I get 2 pi here. Cancel 2. I get negative radical 3. Half times half is a quarter. Plus radical 3 over 4. Minus 3 and 3 get cancelled. 2 and 2 get cancelled. I get pi. Cancel 2. I get minus radical 3. Half times half is a quarter. Double negative is positive, so I get positive radical 3 over 4. Then 2 pi minus pi is pi. Negative radical 3 plus negative radical 3 is negative 2 radical 3. Radical 3 over 4 plus radical 3 over 4 is radical 3 over 2. If I combine like terms here, I have pi minus 3 radical 3 over 2. That's an area. That's a final answer. That's an area enclosed by the inner loop. That's an area enclosed by the inner loop. Next example. In the previous problem, find the area enclosed by the outer loop. Find the area enclosed by the outer loop. So we're looking for area enclosed by the outer loop. For the outer loop, theta first of all is from 0 to 2 pi over 3. Then you complete half of an outer loop. It starts the inner loop. At 4 pi over 3, it go out from the inner loop. It starts again from the outer loop. So from the outer loop, theta is from 0 to 2 pi over 3. Then take a break from 4 pi over 3 to 2 pi. So theta is from 0 to 2 pi over 3. Then take a break from 4 pi over 3 to 2 pi. So for area of an outer loop, we have integral theta from 0 to 2 pi over 3, half of 1 plus 2 cosine theta squared d theta, plus integral from 4 pi over 3 to 2 pi, half of 1 plus 2 cosine theta squared d theta. That's an area enclosed by an outer loop. It's first of all from 0 to 2 pi over 3. take a break, then continue at 4 pi over 3, from 4 pi over 3 to 2 pi. That's an area enclosed by the outer loop. But here, this integral is harder enough. Solving two integrals may be too complicated. This integral itself is harder enough. Solving two integrals may be too much work. Can we do this in one integral? Can we do this in one integral? If we consider negative angles, if I rotate this way, the angle will be negative. If I rotate this way, angle will be negative. For 4 pi over 3, the negative angle is negative 2 pi over 3. Take 4 pi over 3 minus 2 pi. That's the negative coterminal angle. Take 4 pi over 3 minus 2 pi. That's the negative coterminal angle. So the integral from 4 pi over 3 to 2 pi let me write it, half of r squared d theta. The area from 4 pi over 3 to 2 pi is the same as the area from negative 2 pi over 3 to 0. Half of r squared d theta. Can anybody see that? From 4 pi over 3 to 2 pi is the same as the integral from negative 2 pi over 3 to 0. So this is the same as integral from negative 2 pi over 3 to 0. Now we have area from negative 2 pi over 3 to 0, then 0 to 2 pi over 3. Now what we have here is from area from negative 2 pi over 3 to 0, and then from 0 to 2 pi over 3. That's what we have so far. That's what we have right now. From negative 2 pi over 3 to 0, from negative 2 pi over 3 to 0, then from 0 to 2 pi over 3, which can be noted as one integral from negative 2 pi over 3 to 2 pi over 3. By this formula, integral from a to b f of x dx plus integral from b to c f of x dx. That's the same as integral from a to c f of x dx. Area under the curve from a to b, then from b to c is the same as area under the curve from a to c. So here what we have is from negative 2 over 3 to 0, then from 0 to 2 over 3. That's the same as integral. That's the same as the integral from negative 2 pi over 3 to 2 pi over 3. Half of 1 plus 2 cosine theta squared d theta. So this two integral is the same as this one integral. Solving one integral will be much easier than solving these two crazy integrals. Next, take antiderivative. We know that this function and this function, they are exactly the same. For number 5 and number 6, the integrand here is exactly the same. So their antiderivative must be the same. We found antiderivative already in problem number 5. This is the antiderivative of this function. That means this is also the antiderivative of this function. So let me use the antiderivative from problem number 5. The antiderivative here is 3 over 2 theta plus 2 sine theta plus half of sine 2 theta. Evaluate from negative 2 pi over 3 to 2 pi over 3. When we plug in 2 pi over 3, which we have it already, when we plug in 2 pi over 3, we get this part. When we plug in 2 pi over 3, we get this expression here. So when we plug in 2 pi over 3, we get 3 over 2 times 2 pi over 3 plus 2 times radical 3 over 2 plus half times negative radical 3 over 2. That's what we get when we plug in 2 pi over 3. When we plug in negative 2 pi over 3, I get 3 over 2 times 2 pi, negative 2 pi over 3 plus 2 times sine negative 2 pi over 3. What's sine negative 2 pi over 3? Negative 2 pi over 3 is here. That's the reference angle. This is negative pi. If we go counterclockwise, this is negative pi. Angle between negative 2 pi over 3 and negative pi is pi over 3. So the reference angle is pi over 3. Sine function in quadrant 3 is negative. Sine pi over 3 is radical 3 over 2. So you got negative radical 3 over 2 for sine negative 2 pi over 3. Next, if I plug in negative 2 pi over 3 for sine 2 theta, 2 times negative 2 pi over 3 is negative 4 pi over 3. So you try to find sine of negative 4 pi over 3. Negative 4 pi over 3, somewhere here. That's negative 4 pi over 3. If we rotate counterclockwise, that's negative 4 pi over 3. And that's the reference angle. Reference angle is an angle between the terminal side and the x-axis. So angle between negative 4 pi over 3 and pi is pi over 3. Reference angle is pi over 3 here. This angle terminates in quadrant 2. Sine function in quadrant 2 is positive. So we get positive sine pi over 3. Sine pi over 3 is radical 3 over 2. So sine of negative 4 pi over 3 is positive radical 3 over 2. So we get positive radical 3 over 2 here. Then adding up. Cancel 2, cancel 3, I get pi from the first term. Cancel 2, I get radical 3. Half times negative radical 3 over 2 is negative 1 over 4 times radical 3. Cancel 2, cancel 3, I get negative pi, which is positive pi. Cancel 2, double negative become positive, I get positive radical 3. Half times half is a quarter, and we have negative radical 3 over 4. Then combine like terms. Pi plus pi is 2 pi. Radical 3 plus radical 3 is 2 radical 3. Negative radical 3 over 4 plus negative radical 3 over 4 is negative radical 3 over 2. If I combine like terms, I get 2 plus 3 radical 3 over 2. That's an area enclosed by the outer loop. That's an area enclosed by an outer loop. Next example, let R1 equal to 3 sine theta and R2 equal to 1 plus sine theta be two polar curves. Find the area of the region inside the first curve but outside the second curve. So let's draw the picture first. First curve, R1 equal to 3 sine theta. How does the curve looks like? Let's plot some points. Make table for R and theta. Let's try 0, pi over 2, pi, 3 pi over 2, and 2 pi. Let's try this 5 point first. See if we get a curve. When plotting 0, sine 0 is 0. When plotting pi over 2, sine pi over 2 is 1. I get 3. When plotting pi, I get 0. When plotting 3 pi over 2, I get negative 1. 3 times negative 1 is negative 3. When plotting 2 pi, I get 0. Let's plot points. When theta is 0, that's in a positive direction. R is 0, the point is here. When theta is pi over 2 is here. That's in a positive direction. R is 3, 1, 2, 3, the point is here. When theta is pi, that's in a positive direction. R is 0, the point is here. When theta is 3 pi over 2, 3 pi over 2 is here. Radius is negative 3. That's positive direction, so negative 3 is 1, 2, 3, we are here. When theta is 2 pi, we go back to 0. It looks like it goes back and forth between 2 points. We can sketch a graph by this, like this. So that means we need to plot more points. Let's find some point between 0 and pi over 2. Let's find some point between 0 and pi over 2, and some point between pi and 2 and pi over 2. Let's find some value for pi over 4 and 3 pi over 4 here. Let's try pi over 4, pi over 2, 3 pi over 2, and pi. If I plug in pi over 4, sine pi over 4 is radical 2 over 2. Radical 2 over 2 times 3 is 3 radical 2 over 2. If I plug in pi over 2, sine pi over 2 is 1. I get 3 here. If I plug in 4 pi over 3 pi over 4, sine 3 pi over 4 is radical 2 over 2 times 3 is 3 radical 2 over 2. If I plug in pi, sine pi is 0. So when theta is pi over 4, I get 3 radical 2 over 2. That's about 2.1, a little more than 2. 1, 2, somewhere here. 3 radical 2 over 2 is about 2.1, somewhere here. Connect this point using smooth curves. It looks like a circle. It looks like a circle. Now, does the curve repeat itself if we continue? Let's test one more point, see if the curve repeats itself. If I try 5 pi over 4, sine 5 pi over 4 is negative radical 2 over 2, times 3 is negative 3 radical 2 over 2. Let's test one more point, see if the curve repeats itself. Sometimes, if a curve complete one loop, it could be a figure A. It could be a figure of A. Sometimes when a curve complete one loop here, it could be a figure of A. So be very careful. Let's test one more point. See if the curve repeats itself. Sometimes when the curve complete one cycle here, it could be a figure of number A. Be very, very careful. If we plug in 5 pi over 4, we get negative 3 radical 2 over 2. This is the direction 5 pi over 4. In this direction, r is positive. But here, since r is negative, it goes to an opposite direction. Negative radical 3 over 2. Negative 3 radical 2 over 2. So the curve repeats itself. After pi, the curve repeats itself. So we don't need this. That's the circle for R1. That's the graph for R1. That's the graph for R1. That's a circle. Diameter is 3. Next, let's graph R2. Let's graph R2. R2 is 1 plus sine theta. Let's plot some value for theta. Let's try 0, pi over 2, pi, 3 pi over 2, and 2 pi. When theta is 0, sine 0 is 0, 1 plus 0 is 1. Sine pi over 2 is 1, 1 plus 1 is 2. If I plug in pi, sine pi is 0, 1 plus 0 is 1. If I plug in 3 pi over 2, sine 3 pi over 2 is negative 1, 1 plus negative 1 is 0. If I plug in 2 pi, sine 2 pi is 0, 1 plus 0 is 1. That's plot points. When theta is 0, r is 1. That's the first point. When theta is pi over 2, r is 2. Pi over 2 is here. That's in the positive direction. R is 2, 1, 2. When theta is pi, r is 1. Pi is here. R is 1. Connect 3 points using smooth curves. That's the direction. When theta is 3 pi over 2, that's 3 pi over 2. That's in the positive direction. R is 0. Connect 3 points with smooth curve. Let's continue the curve. Connect 3 points using smooth curves. When theta is 2 pi, r is 1. Point is here. Looks like a heart shape. Looks like a heart shape. We have a heart shape. We have a circle. Next, let's draw two pictures together. We have a circle. And we have a heart shape. This point is 2. This point is 3. So that's R1. The circle is R1. The heart shape is R2. This upside down heart is R2. The circle is R1. And this upside down heart is R2. We are looking for area inside the first curve, but outside the second curve. Inside the first curve, but outside the second curve. It should be this part. Area inside the first curve, but outside the second curve. So, what can we do here? Area inside the first curve, outside the second curve. Let's find these 2 points first. Let's find their intersection first. For the intersection, I set R1 equal to R2. In order to find the intersection, I set R1 equal to R2. So for intersection first, set R1 equal to R2. Set 3 sine theta equal to 1 plus sine theta. Solve the equation for theta. I can subtract sine theta from both sides. I get 2 sine theta equal to 1. Then divide both sides by 2. Sine theta equal to half. Solve the equation for theta. Solve the equation for theta. Let's find the reference angle first. Reference angle is inverse sine of half. We know sine 30 degrees is half. That means sine pi over 6 is half. So inverse sine of half is pi over 6. That's the reference angle. Here, sine function is positive. We know that sine function is positive in quadrant 1 and quadrant 2. Sine function is positive in quadrant 1 and quadrant 2. If theta belong to quadrant 2, belong to quadrant 1. If theta belong to quadrant 1, angle theta is the same as the reference angle, which is pi over 6. if theta belongs to quadrant 2, theta is pi minus the reference angle, which is 5 pi over 6. Pi minus pi over 6 is 5 pi over 6. That's theta. That's the theta when theta lies in quadrant 2. So we have two solutions, pi over 6 and 5 pi over 6. That means at this point, theta is pi over 6. At this point here, theta is 5 pi over 6. In order to find the shaded area here, we try to find area enclosed by the further curve minus an area enclosed by the closer curve. We try to use an area bounded by the further curve minus an area bounded by the closer curve. This is a closer curve. This is further curve. We try to use area bounded by the further curve minus an area bounded by the closer curve. So area for an area region, we try to find area bounded by the further curve. Further curve is R1. Further curve is R1. And the limit is from pi over 6 to 5 pi over 6. Half of R1 square dx d theta. That's area bounded by the further curve minus the area bounded by the closer curve. R2 is the closer curve. Use area bounded by the further curve minus area bounded by the closer curve, and take the integral from pi over 6 to 5 pi over 6. That's the shaded region. Then for these two integrals, see they have the same limit. I can combine them together. For these two integrals, see they have the same limit here. I can combine them together. I have integral from pi over 6 to 5 pi over 6. Half of R1 square minus half of R2 square d theta. I can pull out half. Half is a common factor. I can pull out half. What's left is R1 square minus R2 square. Then plug in R1 and R2. R1 is 3 sine theta. R2 is 1 plus sine theta d theta. Then expand the perfect squares and combine like terms. Expand the perfect squares and combine like terms. I get 9 sine squared theta minus 1 plus 2 sine theta plus sine squared theta d theta. If I combine like terms, 9 sine squared theta minus sine squared theta is 8 sine squared theta. Minus 2 sine theta minus 1 d theta. Then use half angle identity to reduce sine squared theta. Use half angle identity to reduce sine squared theta. Let me continue from here. I have half of integral from pi over 6 to 5 pi over 6. 8 times half of 1 minus cosine 2 theta minus 2 sine theta minus 1 d theta. Eight times half is 4. Distribute 4. I have 4 minus 4 cosine 2 theta minus 2 sine theta minus 1 d theta. If I combine like terms, 4 minus 1 is 3. Then take antiderivative with respect to theta. We have 3 theta minus 4 times half of sine 2 theta. Antiderivative of sine theta is negative cosine theta. We have plus 2 cosine theta. Evaluate from pi over 6 to 5 pi over 6. If I plug in 5 pi over 6, I get 3 times 5 pi over 6. 4 times half is 2. If I plug in 5 pi over 6 here, 2 times 5 pi over 6 is 5 pi over 3. 2 times 5 pi over 6 is 5 pi over 3. Here we have sine 5 pi over 3. What's sine 5 pi over 3? For sine 5 pi over 3, 5 pi over 3 terminates in quadrant 4. Two pi is here. The reference angle is the angle between the terminate side and the x-axis. That's pi over 3. Here, reference angle is pi over 3. This angle terminates in quadrant 4. Sine function in quadrant 4 is negative. Sine pi over 3 is radical 3 over 2. So, sine 5 pi over 3 is negative radical 3 over 2. If I plug in 5 pi over 5 pi over 6 here, I get cosine 5 pi over 6. 5 pi over 6 terminates in quadrant 2. Cosine function in quadrant 2 is negative. And the reference angle for 5 pi over 6 is pi over 6. Cosine pi over 6 is radical 3 over 2. Next, plugging pi over 6, we have three times pi over 6 minus 4 times half is 2. If I plug in pi over 6 here, 2 times pi over 6 is pi over 3. Sine pi over 3 is radical 3 over 2. If I plug in pi over 6 here, cosine pi over 6 is radical 3 over 2. Then simplify. Negative 2 times negative radical 3 over 2 and positive 2 times negative radical 3 over 2, they get cancelled. This is positive radical 3 and this is negative radical 3, they get cancelled. And same thing here, this is negative radical 3, this is positive radical 3, they get cancelled. What's left is half times 5 pi over 2 minus half times pi over 2, which is half, factor half out. I get 5 pi over 2 minus pi over 2, which is 4 pi over 2. 4 pi over 2 is 2 pi. Half times 2 pi is pi. That's an area inside the first curve, but outside the second curve. That's an area of this region here. That's an area of this region here. Answer is pi. Next example, in the previous problem, find the area of the region inside both curves. In the previous problem, we have two curves, R1 and R2. We're looking for the area of the region inside both curves. That's this region here. This region here. We're looking for this region inside both curves. Let me draw a picture. Again. Assume that's R1. R2 is a heart shape It's a heart shape. It's R2. We're looking for the area of the region inside both curves. That's what we are looking for. We're looking for area of the region inside both curves. Let's zoom in, make this region a little larger. Let's zoom in, make it a little larger. If I zoom in the region, the shaded region looks like this. That's the shaded region when I zoom in. This is the origin. This is pi over 6. This is 5 pi over 6. So for the total shaded region, we are looking for area of this region, called is A1. Area of this region, called is A2. And area of this region, called A3. A1 plus A2 plus A3, that's the total area of this shaded region. A1 plus A2 plus A3, that's the total area of the shaded region. How do we find A1, A2, A3 here? For A1, what's the lower bound? For A1, the lower bound here is x-axis. That's the lower bound. That's where this curve is part of R1. R1 starts here as when theta is 0. R1, this is part of R1. This curve is a part of R1. Here, R1 starts at 0. This curve is a part of R2. This curve is a part of R2. This curve is a part of R2. And the last piece here, this is a part of R1. R1 go back to origin when theta is pi. R1 go back to origin when theta is pi. So this curve is a part of R1. This curve is a part of R2. This curve is a part of R1. So together we have 3 pieces. A1 plus A2 plus A3. For A1, the area is from 0 to pi over 6. 0 to pi over 6. Half of R1 square d theta. That's A1. For A2, let's integral from pi over 6 to 5 pi over 6. This curve is part of R2. So A2 is bounded by R2. For A3 here, again, this region is bounded by curve R1. We have 5 pi over 6 to pi. Times half of R1 square d theta, because the region A3 here is bounded by curve R1. So half of R1 square. Now here we can see that the area of the region A1, A3 is the same. The area of these two regions is the same because the curve is symmetrical. So the area of these two regions is the same. So instead of taking these two integrals, I can find area for A1, then multiply by 2. I can find area for A1, then multiply by 2. That's the same as area of A3. So I find area for A1, then multiply by 2. Curve of R1. Curve of R1 is 3 sine theta. Three sine theta square d theta. This represents area of A1 and A3. For area of A2, take integral from pi over 6 to 5 pi over 6. Half of R2 square. R2 is 1 plus sine theta. Then solve the integral. This represents the total area. This represents the total area inside the region bounded by both curves. This represents the area inside both curves. Then solve each integral individually. In the first integral, if I pull out half and 2 get cancelled. Integral from 0 to pi over 6. Let me solve each integral individually, then add them up. 3 squared is 9 sine square theta d theta. Let me solve each integral individually, then add them up. Then use half angle identity. One minus cosine 2 theta d theta. Nine times half is 9 over 2. Take antiderivative. I have 9 over 2 times theta minus half of sine 2 theta. Evaluate from 0 to pi over 6. If I plug in pi over 6, I get 9 over 2 times pi over 6 minus half of 2 times pi over 6 is pi over 3. Sine pi over 3 is radical 3 over 2. If I plug in 0, I get 0. Then simplify, I get 9 over 2 times pi over 6 minus 9 over 2 times radical 3 over 4, which is 9 pi over 12 minus 9 radical 3 over a. That's area of A1 and A3 together. That's the area of A1 and A3 together. Now let me solve the second integral. The second integral is integral from pi over 6 to 5 pi over 6. Half of 1 plus sine theta squared d theta. Expand the perfect square first. I have 1 plus 2 sine theta plus sine squared theta d theta. Then use half angle identity for sine squared theta. That's half of 1 minus cosine 2 theta d theta. Distribute half. Then combine like terms. 1 plus half is 3 half. Then distribute half. We get 3 over 4 plus sine theta minus 1 over 4 cosine 2 theta d theta. Then take antiderivative. We have 3 over 4 theta minus cosine theta minus 1 over 4 times 1 over 2 sine 2 theta. Evaluate from pi over 6 to 5 pi over 6. If I plug in 5 pi over 6, I get 3 over 4 times 5 pi over 6. If I plug in 5 pi over 6 here, I get cosine 5 pi over 6. 5 pi over 6 terminates in quadrant 2. Cosine function in quadrant 2 is negative. Reference angle for 5 pi over 6 is pi over 6. Cosine pi over 6 is radical 3 over 2. Quarter times half is 1 over a. If I plug in 5 pi over 6 here, I got 5 pi over 3. 5 pi over 3 sine 5 pi over 3. Sine 5 pi over 3 is negative radical 3 over 2. We found it in the previous problem. Sine 5 pi over 3 is negative radical 3 over 2. If I plug in pi over 6, I get 3 over 4 times pi over 6 minus cosine pi over 6. Cosine pi over 6 is radical 3 over 2. 1 over 4 times 1 over 2 is 1 over a. If I plug in pi over 6 here, 2 times pi over 6 is pi over 3. Sine pi over 3 is radical 3 over 2. Then multiply out. Here I have 3 and 6 can be reduced as 1 and 2. So I get 5 pi over a. Double negative is positive. Radical 3 over 2 plus radical 3 over 16 minus 3 and 6 can be reduced as 1 and 2. So I get pi over a here. Minus means plus. Radical 3 over 2 minus means plus. Radical 3 over 16. If I combine like terms, 5 pi over a minus pi over a is 4 pi over a, which is pi over 2. Half of radical 3 plus half of radical 3 is radical 3. Radical 3 over 16 plus radical 3 over 16 is 2 radical 3 over 16, which is radical 3 over a. If I combine like terms here, I get pi over 2 plus 9 radical 3 over a. So that's the second integral. That's the second integral. For the final answer, we take the first integral plus the second integral. So for the final answer, we take the first integral, 9 pi over 12 minus 9 over radical 3 over a plus pi over 2 plus 9 radical 3 over a. 9 pi over 12 is 3 pi over 4. Plus minus 9 radical 3 over a get cancelled. Plus pi over 2. 3 pi over 4 plus pi over 2 is 5 pi over 4. That's the final answer. That's the final answer. That's the final answer to this problem. Let me present the area inside both curves. The area inside both curves. Next, let's study arc length of a polar curve. Let r equal to r of theta be a polar curve. Then s equal to r cosine theta. S equal to r cosine theta can be written as r of theta times cosine of theta. And y equal to r sine theta can be written as r of theta times sine theta. Hence, we can consider x and y as parametric equations since they only have one variable theta, since they share the common variable theta. Hence, x and y can be considered as parametric equations with parameter theta. Here, x and y can be considered as parametric equations with parameter theta. Then, the arc length formula for parametric equation. Then, by the arc length formula for parametric equations, we have arc length equal to integral theta from alpha to beta square root of dx over d theta square plus dy over d theta square. That's the arc length formula for parametric equations. Next, we try to rewrite this equation in terms of r and theta. Since x equal to r of theta cosine theta, then dx d theta, if I use product rule for dx d theta, that's derivative of the first times the second plus the first times derivative of the second. That can be rewritten as dr over d theta times cosine theta minus r times sine theta. That's dx over d theta. And similarly for dy over d theta, since y is r of theta times sine theta, if I use product rule here, dy over d theta is again derivative of the first times the second plus the first times derivative of the second. Then that can be rewritten as dy over d theta, dr over d theta times sine theta plus r times cosine theta. Then plugging dx over d theta and plugging dy over d theta. Let's simplify the arc length formula. Try to write it in terms of r and theta. Theta is from alpha to beta. If I plug in dx over d theta is dr over d theta times cosine theta minus r times sine theta. I have dr over d theta times cosine theta minus r times sine theta square plus dy over d theta square. Dy over d theta square is dr over d theta sine theta plus r cosine theta. Dr over d theta sine theta plus r cosine theta. D theta. Then simplify. Let's expand both perfect square first. If I expand both perfect square, I have first one is dr over d theta square times cosine square theta minus 2 times r dr over d theta cosine theta sine theta plus r square sine square theta. That's in the first parenthesis. Now there's not enough room here. Let me put it in the second row. Plus the second parenthesis. Let me put it in the second row. There's not enough room here. Plus dr over d theta square times sine square theta plus 2r dr over d theta sine theta cosine theta plus r square cosine square theta. That's the second parenthesis. Times dr. Sorry, times d theta. Times d theta. Then these two terms get cancelled. They look exactly the same but have opposite sign. For these two terms, they have common factor dr over d theta square. So I pull out common factor dr over d theta square. What's the is? Cosine square theta plus sine square theta. For these two terms, they have common factor r square. If I pull out r square, what's left is sine square theta plus cosine square theta. Times d theta. Then, we know cosine square theta plus sine square theta is 1. Sine square theta plus cosine square theta is 1. So, what's left is integral from alpha to beta dr over d theta square plus r square d theta. That's an arc length formula for polar curve. That's an arc length formula for polar curve. Integral from alpha to beta square root of dr over d theta square plus r square d theta. That's an arc length formula for polar curves. Next, let's look at an example here. Let r equal to cosine theta be a polar curve. Find the length of an arc for one loop. Let r equal to cosine theta be a polar curve. Find the length of an arc for one loop. So let's sketch the graph first. We try to find out for which theta value it complete one loop. R equal to cosine theta. Let's plot some values. Let's plot 0, pi over 2, pi, 3 pi over 2, and 2 pi. Let's see what happens here. If I plug in 0, cosine 0 is 1. Cosine pi over 2, if I plug in cosine pi over 2 is 0. Cosine pi is -1. Cosine 3 pi over 2 is 0. Cosine 2 pi is 1. Let's try to sketch the graph and see how it looks like. When theta is 0, that's the direction. When theta is 0, r is 1. That's the point. When theta is pi over 2 is here. That's the direction. When theta is pi over 2, r is 0. The point is here. When theta is pi is here. R is -1. This is positive direction when theta is pi. When r is -1, it goes in the other direction. That's the point when r is -1. When theta is 3 pi over 2, r is 0. Go back to the origin. When theta is 2 pi, r is 1. 2 pi is here, r is 1. The point is here. It looks like keep going back and forth between these 2 points. We can't sketch a curve. So we need more points in the middle. Let's find more points in the middle. Let's find out what's in the middle when theta is pi over 4. What's in the middle when theta is 3 pi over 4? When theta is 3 pi over 4, when theta is pi over 4, let's make a table over. When theta is pi over 4, cosine pi over 4 is radical 2 over 2. Cosine pi over 2 is 0. Cosine 3 pi over 4 is negative radical 2 over 2. Cosine pi is negative 1. So, when theta is pi over 4, cosine pi over 4 is radical 2 over 2. R is radical 2 over 2. Radical 2 over 2 is about 0.7. 1 is here, 0.7 somewhere here. So that's 0.7. When theta is pi over 2, r is 0. That's here. So connect 3 points using smooth curves. Connect 3 points using smooth curves. Then when theta is 3 pi over 4, that's the direction for 3 pi over 4. R is negative radical 2 over 2. That's the direction for positive R. Since R is negative, we need to go to the other direction. Radical 2 over 2 is about 0.7. So we have negative 0.7 somewhere here. When theta is pi, R is negative 1. That's when theta is pi, R is negative 1. Positive 1 is here, negative 1 is here. So connect 3 points using smooth curves. Connect 3 points using smooth curve. So it looks like when theta from 0 to pi, this curve complete one cycle. When theta from 0 to pi, this curve complete one cycle. So for theta from 0 to pi, this curve complete one cycle. So for arc length, take integral theta from 0 to pi. Then use the formula. Arc length formula is integral from alpha to beta square root of dr over d theta square plus r square d theta. Since r is cosine theta, dr over d theta is negative sine theta. Since r is cosine theta, dr over d theta is negative sine theta. So I have negative sine theta square. Negative sine theta square plus cosine theta square d theta. Then simplify. I have integral from 0 to pi. Negative sine square is sine square theta. Cosine theta square is cosine square theta. Cosine theta square is cosine square theta. Now we add them up. Sine square theta plus cosine square theta is 1. Then antiderivative of 1 is 1 theta. Evaluate from 0 to pi. If I plug in pi, I get pi. If I plug in 0, I get 0. So the answer is pi. So the length of an arc for one loop is pi. Next example. Let r equal to e to the power theta be a polar curve. Find the length of an arc from the origin to the point 1, 0. So then the formula for length of arc is integral from alpha to beta square root of dr over d theta square plus r square d theta. R is e to the power theta. That means dr over d theta, we take derivative, is also e to the power theta. So getting this part is not hard. We have e to the power theta square plus e to the power theta square d theta. Getting this part is not hard. The hardest part is getting the bound here, the upper and lower limit. What's the upper and lower limit here? Now, we're looking for the length of the arc from the origin to the point 1 comma 0. We try to find out the theta value and the origin, and the theta value and the point 1 comma 0. And the origin, what's theta and the origin? And origin, I don't know what theta is, but I know r must be 0. And origin, I don't know what theta is, but I know r must be 0. Then if I substitute 0 for r, I can solve the equation for theta. So I have 0 equal to e to the power theta. We know exponential function is always positive. It cannot be 0. So this 0 must be a little larger than 0. It cannot be exactly 0. This 0 cannot be exactly 0. Exponential function is always positive, so it must be 0 but a little larger than 0. Then in order to solve for theta, we apply ln on both sides. Apply natural log on both sides. Here I get theta by itself. What's natural log of 0? What's natural log of 0? Natural log looks like this. It's y equal to ln of x. When s approaches to 0 from right side, when s approaches to 0 from right side, natural log function approaches to negative infinity. When s approaches to 0 from right side, natural log approaches to negative infinity. Here, since negative infinity is not a real number, so we say as theta approaches to negative infinity, the polar curve approach to the origin. So we say as theta approach to negative infinity, the polar curve approach to the origin, since infinity is not a real number. Next point, 1 comma 0. At point 1 comma 0, let's find r first. In order to find theta, let's find r first. At point 1 comma 0, what's r? R is, we know r squared is x squared plus y squared. R squared is x squared plus y squared. So r squared equal to 1. Here, to make it easier, we consider r is positive. R is square root of 1, which is 1. So at point 1 comma 0, r is 1. Once I know what r is, we can solve an equation for theta. So I have 1 equal to e to the power theta. Apply ln to both sides. Apply natural log to both sides. Natural log of 1 is natural log of e to the power theta. Natural log of 1 is 0. So theta is 0. At point 1 comma 0, theta is 0. And the origin, theta approach to negative infinity. So here, this arc length. And the origin, theta is negative infinity. At point 1 comma 0, theta is 0. Then solve this integral. Now let me solve the integral here. First of all, this is an improper integral. We first of all need to write it as a limit. T approach to negative infinity. Integral from t to 0. E to the theta square is e raised to 2 theta. E to the power of theta square is e to the power of 2 theta d theta. Combine like terms, I get square root of 2e to the power of 2 theta d theta. This square root can be rewritten as square root of 2 times e to the power of theta d theta. This square root can be rewritten as square root of 2 times e to the power of theta. When you take square root, you divide the power by 2. Then square root of 2 is constant. We leave it the same. Take antiderivative. E to the power theta. The antiderivative is the same as e to the power theta. evaluate theta from t to 0. If I plug in 0 for theta, I get e to the power 0 here. If I plug in t for theta, I get e to the power of t. Then take a limit. When t approaches to negative infinity, we have e raised to negative infinity here. What's e raised to negative infinity? Look at the curve of e. The graph of e looks like this. That's y equal to e to the power of x. When x approaches to negative infinity, when x approaches to negative infinity, e of x will approach to 0. When x approaches to negative infinity, e of x will approach to 0. So when t approaches to negative infinity here, e of negative infinity is 0. So we have square root of 2 times e to the power 0. E to the power 0 is 1 minus 0, which is 2. So that's the length of arc.